Okay, our next unit is stoichiometry. Stoichiometry is the quantitative study of chemical changes that involves the mass relationships between the reactants and the products in a chemical reaction. Let's break down what that means. This is from the first 6 weeks here. Quantitative means that it has to do with numbers, okay? So we're going to actually be dealing with numbers rather than characteristics or something. What stoichiometry is going to allow us to do is to calculate information of a substance that we don't know anything about. Okay, we could know something about one substance, but this is going to actually let us calculate information about a completely different substance. Okay, so the key to stoichiometry is knowing when to use it. Okay, that's kind of the key to everything. And one way that we can recognize that we're looking at a stoichiometry problem is if we're given information about one substance, but then they ask us for information about another substance. If you recognize that that's happening, then you are definitely looking at a stoichiometry problem. You are going to need the balanced chemical equation in order to do stoichiometry. In fact, at this point in the course, there is not a single instance in which you can leave a chemical equation unbalanced. Okay, so if you have an unbalanced chemical equation from now on, you need to balance it. That should be one of your very first steps. Okay, so here are kind of the rules to solving a stoichiometry problem. Number one, you need the balanced equation. Number two, you're going to convert the given amount into moles. If it's already in moles, then cool, they did some of the work for you. If it's in grams or something else, then you're going to have to make sure you get it into moles. Then you're going to use the balanced chemical equation to convert from moles of one substance to moles of another substance. And then finally, you'll convert to your desired units. Something I haven't told you yet about a balanced chemical equation is that the coefficients of a chemical equation are in units of moles. So let's do an example problem. If iron pyrite, FeS2, is not removed from coal, oxygen from the air will combine with both the iron and the sulfur as the coal burns. If a furnace burns an amount of coal containing 100 grams of iron pyrite, how many grams of sulfur dioxide, an air pollutant that causes acid rain, is produced? Okay, well, let's notice that they gave me information about iron pyrite here, but then they asked me for information about sulfur dioxide. So that means that this must be a stoichiometry problem because I got information about one substance, but I was asked for information about a different substance. Okay, so step one, the very first thing we need to do is to balance our equation. Alright, so take a second. Let's review our balancing thing, see if you can figure out what the balancing coefficients are for our equation here. Okay, so here's what I got. I don't care which method you used, either inspection or algebra, but this is what you should have come up with. Alright, now these balancing coefficients here I told you are the molar values of the substances behind them. Okay, so what that means is that we can use this as a conversion factor. Remember back when I taught you the algebra method, I told you that this arrow here kind of represents an equal sign, right? And I told you back in the first 6 weeks, if you ever see one thing equaling another thing, then you are looking at a conversion factor. So we could say that 4 moles of this iron pyrite here is equal to 8 moles of sulfur dioxide. See, here's the equal sign. 4 moles of this is equal to 8 moles of that. Alright, so that's a conversion factor that allows me to move from information about iron pyrite into information about sulfur dioxide. Okay, let's look at step 2. Alright, step 2 says that we need to write the mass information given in the problem. What they just mean is put the given over 1. Okay? Okay. Step 3 now says that we need to convert grams of the iron pyrite into moles of the iron pyrite. Alright, let's do that. Now we're going to use our balanced chemical equation to change from moles of iron pyrite to moles of SO2. So here's our conversion factor again, okay? Remember, 4 moles of iron pyrite is equal to 8 moles of SO2. And now we're going to convert the moles of SO2 into grams of SO2 because that's what they asked for. Okay, so now the last part, step 6, we have figured out all of the stoichiometry part of this. All of our units cancel out now, and all we have to do is multiply across the top and divide across the bottom to figure out our grams of sulfur dioxide. Okay, so we come up with 106.79 blah blah blah. But with our significant digits, our given only has one sig fig. That means we have to stop right here. So we get 100 grams of sulfur dioxide as our answer. Alright, let's see here. This is the step 2. Okay, step 1 was doing our balanced chemical equation, and then this right here is step 2, converting from the given into moles. And then step 3 is to use the balanced chemical equation to change from one substance to another. And then the last step is to change from the moles to the desired unit for your product there. Okay? So we're going to do these same steps over and over and over again. Alright? The chemical equation, grams to moles, use the balanced chemical equation, convert to the desired unit. Okay? So just memorize those steps and you get the problem right every single time. Okay, so the process that we just went through is for ideal stoichiometric problems because it assumes that every little bit of reactants will be converted into products. Now, this word ideal here, that means perfect. So, is this situation ever true? In other words, do we live in a perfect world where we will change every bit of the reactants into products? No, that situation is never true. You cannot change 100% of reactants into products because no process is 100% efficient. Here's what I mean by that. Let's pretend, for example, that we have one test tube filled with some liquid and we have another test tube filled with some more liquid. What happens after the test tube has completely been tilted upside down over the top of this Erlenmeyer flask? Will every little droplet of liquid leave the bottom of the test tube, or will some of the liquid still be in the bottom of the test tube at the end? Of course, there's going to be liquid still left in there. And that means that all of the reactants did not make it into the reaction, and therefore you can't make 100% of the products. That's true anytime you change from one container to another. You are always going to leave something behind. Okay, and that is where you lose product. So in your experiments, anytime that you pour a substance from one thing to another, or you transfer a substance, maybe it's a solid, from one container to another, you're going to lose some products. So you want to make as few transfers as possible. Okay, so what's the point then? We don't live in a perfect world. We're never going to be able to get 100% of the products, so why do we even have to learn about stoichiometry if that doesn't even apply? It's still a valuable calculation because it lets us see what the maximum could be in a perfect world, and then we can gauge how close are we getting to perfect. It lets us know if we have a good reaction setup or if there's a problem with our setup. Just because you don't get close to 100% of the product doesn't mean that you're doing a bad job. It might mean that there's a leak somewhere in your lab equipment, or it might mean that you spilled something, or that you've got too many transfers going on. There's a whole bunch of different scenarios, and this stoichiometry just allows you to notice that something might be going wrong with your experiment. Okay, let's do another practice question here. We have how many grams of oxygen are produced when 10 grams of potassium chlorate are completely decomposed? Notice that they gave me information about potassium chlorate, but then they asked me for information about oxygen. Okay, so that tells us that this is a stoichiometry question, and then here I've given you a hint because we're still getting used to this. Remember, the first step for stoichiometry, you need to predict and balance the equation. You might not always have to predict, but in this case you do because I didn't give you the formula. Okay, but I did tell you that you are decomposing potassium chlorate. So see if you can remember how to do that. Okay, here's what you hopefully came up with, and now we can convert our given grams into moles. Okay, and then we need to do step 3, where we use the balanced chemical equation to convert from moles of the potassium chlorate into moles of the oxygen. And then our last step is to figure out how many grams of oxygen there are. So we're going to go from moles of oxygen to grams of oxygen. Okay, so here we've converted from moles of oxygen to grams, and then we've multiplied across the top, divided along the bottom, and this is how many grams of oxygen we come up with. Of course, our given only has 3 sig figs, which means our final answer can only have 3 sig figs. So we come up with 3.92 grams of oxygen as our answer. If we review our steps, step 1 is to do the balanced chemical equation. Okay, then here we have step 2, which is to convert from grams to moles. Then we have step 3, which is to use the balanced chemical equation. And then we have step 4, which is convert to our desired units. Okay, so it's always the same 4 steps. Okay, let's look at one more practice question. In the movie Apollo 13, the astronauts built what is known as a carbon dioxide scrubber to remove carbon dioxide from the air using lithium hydroxide. The following equation shows the reaction. CO2 plus 2 LiOH yields Li2CO3 plus H2O. How many moles of lithium hydroxide are required to react with 20 moles of CO2, the average amount exhaled by a human each day? Okay, so if you haven't seen this movie, you really need to. It's awesome. But what happened up on the Apollo 13 spacecraft is they filters in the spaceship started malfunctioning. And so the levels of CO2 in the cabin started increasing, which means that the astronauts weren't getting enough oxygen and they would eventually die. So they radioed down to NASA and they said, this is what's happening and can you help us out? So the NASA chemists and engineers got together to figure out how to build a CO2 scrubber, which is something that removes carbon dioxide from the air using only the stuff available to the astronauts. Once they figured it out, they told the astronauts how to do it, and then they had to do it up on the spacecraft. Now we want to know how many moles of this lithium hydroxide can remove 20 moles of carbon dioxide. Okay, you have your given here. You were given information about carbon dioxide, but you were asked for information about lithium hydroxide. I want you to see if you can do this question from start to finish all by yourself. And we'll see if you got what I got when we come back. Okay, so hopefully you came up with what I did. We put our 20 moles of carbon dioxide over 1, that's our given, and then we would normally convert from grams to moles, but they gave us moles to start with, so they already did step 2 for us. The third step is to use the balanced chemical equation to change from moles to moles. So we changed 1 mole of carbon dioxide into 2 moles of lithium hydroxide. And then we would normally convert into grams. However, they asked me how many moles of lithium hydroxide. So we stop right here. All you have to do is multiply across the top, divide across the bottom, and we come up with 40 moles of lithium hydroxide as the answer. Okay, the next thing we're going to talk about is percent yield. We have a theoretical yield, and this is what you get when you do stoichiometry. Okay, so at the end of every stoichiometry question that you ever do, you are finding the theoretical yield of a substance. Okay, it's called theoretical yield because that's only what you would get in a perfect world. Okay, we have the actual or experimental yield, and that's what you get in real life. So you go back in the lab, you actually perform the experiment, and whatever you really get in real life, that would be your actual or experimental yield. Remember that no process is 100% efficient, and so your actual yield is never going to equal your theoretical yield. You cannot get 100%. Okay? So what we want to find is percent yield. We want to know what the percentage is that we are getting towards 100%, or the theoretical yield. Okay, so the percent yield tells us how close to perfect we got. And this has to do with our efficiency. Okay, did the reaction that we performed in the lab have a high efficiency, meaning that we produced almost 100% of the product? Alright, so here's your formula for percent yield, and yes, you need to memorize it. Percent yield is equal to the actual yield, or the experimental yield, divided by the theoretical yield, and times 100. Alright, so let's do a practice question. We have 45 grams of hydrochloric acid is reacted with magnesium hydroxide. Write the balanced equation below. Alright, so I've given you both of your reactants here. You should be able to predict the products and then balance the equation. Take a second and see if you're still able to do that. Okay, so here is our reaction, and it's all balanced. Here's the question. Suppose in the reaction above, a chemist actually obtained 55.4 grams of magnesium chloride. Okay, now they're telling you right here that this is the actual yield that you would be given in a problem. I won't always do that. You're going to have to recognize when it tells you they obtained an amount, they're telling you the actual yield. Calculate the percent yield of magnesium chloride that the chemist obtained. And here's another hint for you. You need to know the theoretical yield. Okay, so if you want the percent yield, remember the formula. It's actual over theoretical times 100. So you need the theoretical yield. They've given you the actual. Where do you get the theoretical yield from? Right here, we learned that the theoretical is what you get from stoichiometry. So you need to do the stoichiometry on this in order to get the theoretical yield. Okay, so how do I do that? Well, you need the theoretical yield of magnesium chloride. Okay, up here, they told you that you had 45 grams of hydrochloric acid, and now you need to know how many grams of magnesium chloride you could make. That will give you your theoretical yield. So they gave you information about one thing, they asked you for information about another, so you can do your stoichiometry on this. So we've already done step 1, which was to balance the chemical equation. Step 2 is going to be to change grams of hydrochloric acid into moles. Okay, then the next step is to use the balanced chemical equation to convert from mole to moles. So we're going to convert from hydrochloric acid to magnesium chloride. So 2 moles of this are equal to 1 mole of that. And now we just need to do step 4 and convert moles of the magnesium chloride into grams of magnesium chloride. Alright, and now all we have to do is multiply across the top and divide along the bottom. Okay, so here is our theoretical yield of the magnesium chloride. So what we're going to do with that now is plug it into our percent error formula. Okay, so here's our percent error formula. Remember that it is actual over theoretical times 100. This is not the actual amount of the magnesium chloride. This is the beginning amount of your hydrochloric acid, so please don't make the mistake of trying to put that in here. I know some people do that. This is your actual amount of the magnesium chloride. So that's going to go here, and this is your theoretical amount of magnesium chloride that we just got from doing our stoichiometry. So now we just have to do the math. So that gives us 94.2905, and there's a whole bunch of more numbers. But since our beginning information, our given, had just 3 sig figs, then that means that our answer can only have 3 sig figs. So we come up with 94.3% magnesium chloride. And yes, you do need to include the percent sign, and you need to say what it is the percent of, and we were finding percent of magnesium chloride. This is considered the unit for your answer, and so without it, it's a naked number, and we're going to have to mark it wrong. Alright, let's continue our discussion of stoichiometry. The next section is going to deal with what we call limiting reagents. When we do a reaction, one of the reactants is going to be what's called a limiting reagent because it limits how much product can be made. And the way that it limits it is because it's the thing that runs out first. And once that reactant is all used up, the reaction can't happen anymore. So we call it the limiting reagent. Reagent is just another word for reactant. We're also going to familiarize ourselves with words like consumed. If something is totally consumed, all that means is that it's all used up. And then we're left with what's called an excess reagent. That's the stuff that's not totally consumed, the leftovers. Okay, so let's take a look at this situation here just to kind of help familiarize ourselves with this idea. We want to figure out what is the limiting and what is the excess reagent. Okay, we have 8 car bodies here and we have 48 tires. Okay, so if every car requires 4 tires, then how many cars can we actually make? Well, if we base it off of the tires, 48 divided by 4, we should be able to make 12 cars. But we only have 8 car bodies. So which one of these is going to run out first, the car bodies or the tires? Okay, hopefully you picked the car bodies were going to run out first. That means that the car bodies are the limiting reagent and the tires are the excess reagent. Okay, let's look at another example. Let's say that we have an airplane that has 350 seats available and there are 400 people that want to take a trip on the airplane. Is that possible? What is the limiting factor in this example? Okay, hopefully you should recognize no, that's not possible, and the limiting factor is the number of seats on the plane. The excess is the number of people. Alright, one more. Let's say that we have a manufacturer of bicycles and they have 5,050 wheels, 3,013 frames, and 2,455 handlebars. How many bicycles can be manufactured, and which of those parts is the limiting reagent? Okay, well first off, every bicycle has to have 2 wheels. That means that we need to divide this number by 2 to see how many bikes we could make based off of the wheels. Okay, we could make 2,025 bikes based off of the number of wheels that we have. How many bikes could we make based off of the number of frames that we have? 3,013. Since every bike needs 1 frame, then we can make that number of bikes based off of the number of frames that we have. Okay, and now how many bikes can we make based off of the number of handlebars that we have? Since every bike needs just 1 set of handlebars, we can make 2,455 bikes. Okay, so which number is smaller? This number right here is the smallest. That means that the wheels are the limiting reagent because they're going to get used up first, and they limit the number of bicycles that we can actually make. So I'm always in the habit, and I want you to also, anytime you finally figure out what the limiting reagent is, go ahead and label it. Okay, so then how many bikes can we actually manufacture? It would be this number right here. Okay, so now we're going to get into the actual chemistry stuff, since hopefully you understand what a limiting reagent and what an excess reagent is a little bit more now. The first step to solving any limiting reagent problem is being able to recognize that you are looking at a limiting reagent problem. And here's how you recognize it. Anytime that you are given the amount of more than one reactant, that's the beginning material, you must determine which one of those is the limiting reagent. In other words, which one of those reactants is going to get used up first. Okay, so let's do a practice problem here. A 50.6 gram sample of magnesium hydroxide is reacted with 45 grams of hydrochloric acid. Okay, first off, we need to write out our reaction, and then we need to balance it. So let's do that. Okay, so here we have our balanced chemical equation, and now we need to decide if this is a limiting reagent problem that we're looking at. Okay, so one of the very best ways to find out if you're looking at a limiting reagent problem is to write down what you know about the components of the reaction. In other words, any given information that they give you about any of the compounds in the equation, write down that information underneath that compound. Alright, so you'll notice that we were given information about more than one reactant. That automatically means this is a limiting reagent question. So when we are asked what is the theoretical yield of magnesium chloride, we actually have to figure out which one of these is going to run out first. And whichever one of them runs out first, that's the one we need to base our answer on. Now, one thing I want you to be careful of is that you cannot tell, and you should not jump to any conclusions about which thing is going to be running out first just by looking at the amount of grams that you were told. So, just because it looks like there's more magnesium hydroxide than there is hydrochloric acid does not necessarily mean that the hydrochloric acid is the limiting reagent. It doesn't mean that it's not, but it for sure doesn't guarantee that it is. The reason for that is that this stuff is not really based off of the grams, it's based off of their molar ratio to each other. Notice that there's twice as much hydrochloric acid than there is magnesium hydroxide. So until you do the math, you can't really figure out which one's going to run out first. So here are the rules to figuring out which one's the limiting reagent. You're going to use each reactant's given mass or number of moles if they give you moles to start with. Then you're going to calculate the amount of product that can be made using the balanced chemical equation. And then whichever one creates the smallest amount of product, that's the limiting reagent. Now you get to pick whichever product you want on the other side, but if you're smart, then you'll try and kill two birds with one stone, and you'll pick the product that they ask you about later on in the question. So you'll see here they asked for the theoretical yield of magnesium chloride. In order to find out the limiting reagent, which one of those it is, I could pick either product I want. I might be tempted to pick water because it's more easy to calculate the molar mass of water than it is of magnesium chloride, because I happen to have hydrogen and oxygen's molar mass memorized already. But they actually asked me about the yield of magnesium chloride, so there's no sense in basing my limiting reagent calculation off of water and then have to do it all over again for magnesium chloride. So I'm going to pick the magnesium chloride as the product. Okay, so here is the theoretical yield for magnesium chloride based off of magnesium hydroxide as the starting material. Now we're going to do the entire process all the way through again, except we're going to start with hydrochloric acid as the starting material and see how much magnesium chloride we can make. Okay, and here we have the theoretical yield of magnesium chloride based off of hydrochloric acid being the starting material. So if we compare the two numbers, you'll see that the 58 grams is less than the 82 grams. that means that the hydrochloric acid must be the limiting reagent. This is going to run out first, and so it produces a smaller amount of the magnesium chloride. Again, we could have chosen any product we want, but it made sense to choose magnesium chloride because that's what it asked me for. And once we've made that choice, you have to use the same one for both of your calculations. So the smaller amount is the theoretical yield of magnesium chloride. So we need to come up with the correct answer with sig figs. Alright, and so we have 58.8 grams of magnesium chloride as our theoretical yield. Alright, I want to review this process with you real quick one more time, okay? When we are asked about the theoretical yield of something, and we have information about more than one reactant, it's a limiting reagent problem. That means you have to figure out which one is limiting and which one is excess. We just figured out, by the way, that the limiting reagent is the hydrochloric acid and the excess reagent is the magnesium hydroxide. Okay, so if you have information about both, you need to do your stoichiometry calculations twice. One for one reactant and one for the other. You pick any product that you want, but if you're smart, you'll pick the product that they ask you about later on in the question. Okay? So we did a calculation based off of magnesium hydroxide first, and we went through the normal stoichiometry. We went from grams to moles. Then we used the balanced chemical equation to get out of moles of magnesium hydroxide and into moles of magnesium chloride. And then we converted to the desired unit, and here's the theoretical yield based off of magnesium hydroxide. Then you do the calculation again with the other reactant. So we went from grams to moles, use the balanced chemical equation to do your mole to mole conversion, then change to the desired unit. Then we have a theoretical yield here based off of hydrochloric acid. You're going to compare these two numbers, and whichever one's smaller must have come from the limiting reagent, and that is going to be the actual answer that you're going to box in. Okay, it's the theoretical yield and it's the correct answer to the question. Just a little bit more information here. If you are ever given a problem that says something like reactant A was reacted with an excess of reactant B to perform product C, what they've actually just done in that question is told you that reactant A is the limiting reagent, since B is the excess reagent. Alright, if B is in excess, that means that B is the excess reagent, and therefore A must be the limiting. Of course, they're not going to have A, B, and C. They'll have actual molecules in there, but if they phrase it that way, with an excess of, then they're telling you that the opposite is the limiting. Alright, let's work a practice question. Silicon dioxide, or quartz, as seen here, is usually quite unreactive, but reacts readily with hydrofluoric acid, according to the following equation. If 2 moles of hydrofluoric acid are exposed to 4.5 moles of silicon dioxide, which is the limiting reactant? Okay, so let's go through this together. Remember, I told you that the very best thing to do is to put information that you're given in the problem underneath that compound in the balanced chemical equation. Alright, and now we need to pick a product. Now they didn't ask for the theoretical yield of any product in particular, so we can choose whichever one we want. So I'm going to choose this silicon tetrafluoride, but you could choose the water just the same. You'll get the same result. Okay, we need to do our stoichiometry calculations with each of these reactants because this is a limiting reagent question. First off, I know that because they actually asked me in the question, and secondly because I see that they gave me information about more than one reactant. Alright, so let's go through the calculations, starting with the silicon dioxide. Okay, so here's our calculations, once with the silicon dioxide as the starting material, and once as the hydrofluoric acid as our starting material. The silicon dioxide starting material tells us that we could produce 4.5 moles of silicon tetrafluoride, and the hydrofluoric acid starting material tells us we could produce 0.5 moles of silicon tetrafluoride. So the smaller answer must come from the limiting reagent. Okay, so the hydrofluoric acid is the limiting reagent, and the silicon dioxide is the excess reagent. Okay, the next thing I want to talk about is the amount of excess reagent that's left over. Okay, we know what the limiting reagent is, we know how to calculate how much product is going to be made based off of our limiting reagent, so really the only thing we don't know yet is how much excess reagent is going to remain. So here's how you're going to do that. If we know the initial amount of the excess reagent, then we can just subtract how much excess reagent gets used up during the reaction, and that will tell us how much excess reagent remains unreacted, or in other words is left over at the end of the reaction. So we're going to continue with our same equation that we've been using throughout the rest of this video series. We've got magnesium hydroxide and hydrochloric acid producing magnesium chloride and water. They've told us that we have our 50.6 grams of magnesium hydroxide and 45 grams of hydrochloric acid. So we need to figure out how to find the amount of excess reagent that's used up. Okay, imagine this for me, please. Let's say that this is the limiting reagent, this is excess, and they're going to combine to form a product over here. Okay, so we'll take one of the limiting and we'll take one of the excess and hook those together. Okay, and then we do it again. And we're going to keep doing this until all of the limiting reagent is used up. Okay, so all of the limiting reagent is used up, and here is the excess reagent that remains unreacted. It's what's left over. If I change my product back into red and green squares, you can see that we've used up 6 of these red squares. So 6 of the excess reagent were used up with 6 of the limiting reagent because they had to bind with each other. Now this case is a little simplified because they're in a 1-to-1 ratio. Over here you see that we have a 1-to-2 ratio, so it would be a little bit different. But the point that I'm making is, in order to figure out how much excess reagent is used up, you have to plan with the limiting reagent. You have to base it off of how much limiting reagent is reacting, because they both come together to form the final product. So, in order to figure out this amount used, we're going to do stoichiometry again. We learned just a little bit ago that the hydrochloric acid was the limiting reagent and the magnesium hydroxide was the excess reagent. So, we're going to put the grams of the limiting reagent over 1. Now, just like always, we are going to convert from grams to moles. Okay, and now the next part, and here is where it's a little bit different than what it's been before. Up until now, after we have balanced the chemical equation, that was step 1, then step 2 is convert from grams to moles, and then step 3 has always been use the balanced chemical equation to do your mole-to-mole conversion. That hasn't changed, that's still what we're going to do. But what we've done up to this point is to take the moles of our reactant and go to moles of a product. But this time, we're not trying to find out any information about a product. We're trying to find out information on how much excess reagent was used. The excess reagent's right here. It's not on the product side. So you're going to be going from one reactant to another reactant instead of going from a reactant to a product this time. Okay, so we're going to go from moles of our limiting reagent to moles of our excess reagent. Okay, and now we just need to have the grams of magnesium hydroxide so that we'll know how much got used up. Okay, now we just need to multiply across the top and divide along the bottom. Okay, so this is the amount of magnesium hydroxide that we will use up in the reaction, okay? We have not actually figured out how much is left over or unreacted. We figured out how much will be used during the reaction. So now we need to figure out how much is going to be left over. And so here's where this formula right here comes into play. You're going to take the initial amount of magnesium hydroxide that they gave you, which was the 50.6 grams, and you're going to subtract the amount that you just calculated down here. This is how much was used up, and that is going to tell you how much remains unreacted. Alright, so we've taken our initial amount, we've subtracted the amount that gets used during the reaction, and we are left with the amount that remains unreacted or left over at the end of the reaction. Okay, so it's a bit of a different kind of process from what we're used to because we're going from one reactant to another reactant instead of a product. You have to go through your stoichiometry in order to find out how much gets used up. And then you need to remember at the end of your stoichiometry, you did not find the amount left over, you found the amount used. So then you need to do your simple subtraction here to figure out how much remains unreacted. Alright, hopefully you understand all of this stoichiometry a little bit more than you did before you started. If you have any more questions, please make sure you come see me for tutorials, and as always, thanks for learning with me today. Bye-bye.